Hello, and welcome to the series of CAEPIPE tutorials. This is the first video of the series that covers the basics of layout building pipe stress analysis using CAEPIPE, a standalone pipe stress analysis software in CAEPIPE 3D+. In this video, we will build a piping system model from scratch, analyze it, and review the results. If you are new to CAEPIPE, don't worry, we got you covered. We'll explain each screen and option as it appears. Before we begin, let's go and download the PDF of tutorial that we shall use as reference for this video tutorial. For that, let's go to our website www.sstusa.com and click CAEPIPE 3D Plus followed by tutorials. You can see multiple tutorials here, more than 35 plus tutorials. For this tutorial, we'll be concentrating on tutorial for modeling and results review using CAEPIPE. Click on Read Tutorial 1 PDF. You can either read the tutorial completely or you can go ahead and download the tutorial. I'm downloading it on desktop. Click Save. Once you have it, we can open the PDF tutorial which is downloaded and review it. We'll go through each step of this tutorial in this video tutorial. Let's go ahead and look at what we are planning to build. The problem has two pipe runs. One is main run starting from node 10 to 50, and then there is a branch run starting from 30 to 80. As shown, the piping network uses A53 grade B material, calcium silicate insulation of 2-inch. It experiences a pressure of 200 psi and 600 degrees Fahrenheit. Content specific gravity is 0.8. Also, the branch run has a diameter of 6-inch standard schedule, and main run has a diameter of 8-inch with 80 schedule. Node 50 is an anchor with specified displacement in y direction, which is vertical. With this, we'll go and build the same in CAEPIPE. For that, let me open CAEPIPE. When you open CAEPIPE for the first time, you'll come up with this frame. This is called as mainframe. You can do multiple things from here, like creating a model, material library, spectrum library, and so on. For now, we'll concentrate mainly on model. As soon as you open CAEPIPE in any given instance, you'll be given with two different windows. One is called the layout window, other one is called the graphics window. Layout window is like a spreadsheet where you will put nodes, elements, supports, and other data. Graphics window shows a 3D view of your piping model as you build it. In the first row, let's type sample problem to start with. This title is not just for documentation but also displays in reports and helps identify your model. The other thing that the PDF tutorial doesn't talk about is the piping code that needs to be selected. Let's decide it as ASME B31.3, which is a process piping code. From the menu, go to Options, click on Analysis. You have multiple tabs here, as you can see, like code, temperature, pressure, dynamics, and MISC. Will not go into other tabs, but concentrate basically the tab code. Code is a tab which talks about the code or standard that we are going to use for this analysis. Since piping design rules differ across industries, CAEPIPE lets you choose relevant codes from here. You can go through all the codes that are available in CAEPIPE for your version of CAEPIPE. For this tutorial, I'll be selecting B31.3 2024. This is a process piping code commonly used in chemical plants and refineries. Click OK to confirm. We'll go through the other tabs of the analysis window in future videos. For the time being, this is enough to start with. Next, we need to define materials for our piping. In the layout windows, click on MATL shortcut for material, or you can go ahead and click on MISC materials, or the shortcut as shown here, that is Control plus Shift plus M, Control plus Shift plus M. All of these three ways will bring you to this window, which is called materials. You can either type the material properties here or choose from CAEPIPE's material library. For this video, we'll choose from CAEPIPE's default material library. To add a material to your analysis, click on material library icon from here. When you are loading this for the first time, you may not have this window coming up. For this window to come up, click on library, and for example, wherever you are, you can go to the installation directory. In my case, it is CSST, CAEPIPE 3D, and material library. You can select from various material libraries that we have here. I will be selecting B3132024.mat. In future, when you click material library icon, you'll always come to this location. From here, you can choose the material that you wish for. In our problem description, it was A53 grade B. I'll select that and click OK. Name it as A53 for easy reference. Once this is done, you can go to defining your sections. Section window can be opened either from MISC sections here or MISC sections from layout window itself. Again, there is a shortcut that is Control plus Shift plus S. Control plus Shift plus S, which will also open the same sections window. Alternatively, you can also click on SECT shortcut for sections from here. Sections represent the pipe sizes, including diameter, schedule, that is wall thickness, piping insulation, etc. You can define multiple sections in your system if you would use them. For now, let's define two sections for this tutorial. In the first row, type 8 and click enter. Select 8 inches from the drop down at nominal diameter and schedule as 80. Doing this will populate the outside diameter and thickness automatically. Click on the insulation and select calcium silicate. Type 2 inches as the calcium silicate insulation thickness. Click OK. You can repeat the process for 6-inch pipe as well. Type 6 and click enter. Choose nominal diameter as 6 inches from the drop down at nominal diameter and schedule as standard. Choose the insulation as calcium silicate and give thickness as 2 inch as well. Click OK. With that, sections have been defined. The other thing that you have to define here is loads. For loads, again, you can either go and click here or use the shortcut Control plus Shift plus L, or you can again go to MISC and click on loads. Alternatively, you can directly click on load from this window here. All of which will get you to this loads window. Here, you can actually define your loads. Loads are the operating conditions that your piping system experiences. These temperatures and pressures will be used to compute stresses and do code compliance. In the first row, type 1 followed by temperature of 600 degrees Fahrenheit as given in the problem statement for T1 and 200 psi for P1 followed by a design temperature of 800 Fahrenheit and design pressure of 250 psi. Specific gravity is given as 0.8. Note that design temperature and pressure should be always greater than or equal to operating temperatures and operating pressures. Close the window. Now, before going further, it's a good practice to save. Click save from here or here. I'll choose desktop as my location. I'm naming it as sample problem 1. Click save. Once that is done, let's go and see what we are trying to model. This is the thing that we are trying to model. So for easy reference, I'll choose a different layout for my screen. I'll keep this to the left. My layout window, I'll decrease it as that. And then graphics window also, I'll decrease it as this. With this setup, I think I can use it easily. As you can see, row 2 already has a node number of 10 with element type as from and data type as anchor. Anchor is a fully fixed support that restrains all movements. In the graphics window, clicking this button will toggle between rendered view and line view. In row 3, type 20 in nodes column, type B and click tab in type. This will automatically change the element type as bent. You can see that the piping layout from 10 to 20 is 9 feet in X direction. Type 9 in DX column and leave DY and DZ as empty. Material, you can either type A53 or you can just click enter and choose the materials that you already defined. In this case, there is only one material that is defined, so select A53. Sections again, you can either type 8 or click enter and choose from the list. You have defined two sections previously that are listed here. Choose 8. Load, again click enter and choose the load that you wish to. That is 1. And this doesn't have any data type. Click enter. Once you do this, you can see an updated graphics window here. As you can see, there is a dashed line from node 10 to node 20. This is because bend is always defined by two elements, element before and after the bend. As of now, we only have one element that is between 10 and 20. Let's go ahead and define the next element. In row number 4, you can either type the node number as 30 or press tab. Pressing tab in the nodes column automatically updates the node number as 30. Leave the type column as blank, which is defaulted to pipe. The bend is in Z direction, which and at a distance of 6 feet. So leave dx, dy empty and type dz as +6 and click enter. Once you do that, you can see few things here. One is the materials section and load column automatically updated based on the previous row values. Further, the graphics window now shows solid lines for 10 to 20 and 20 to 30. You can see the render view here. The other thing is node 30 as a hanger. Go to node 30 row, that is row 4. Click on data's column and click on data. Select hanger from here. Click OK. You can either do that or just while in the cell type HAN, which will automatically select hanger. You can click OK. As you can see, the graphics window is also updated accordingly. Now, node 40 is again at 6 feet from node 30 in Z direction. Go to row 5, click tab. Node 40 is a bend, so type B and click tab, which will automatically update it to bend. Go to leave dx and dy as empty and choose 6 as dz. Click enter. Again, you can see that 30 to 40 is dashed line because bend needs two elements. Let's go ahead and define the next element, which is from 40 to 50, which is a pipe, and 50 has an anchor here. So type tab, it is a pipe, leave that in that way. And now this is going in y direction, negative y direction, because positive y is upward. So negative y direction for 6 feet. So go to dy column and give -6, click enter. This will automatically update the material section and load as described previously. You can see the updated graphics window in a rendered view and line view. As you can see, this is a anchor. Go to the data column in row number 6 and either type A or choose click data and choose anchor from here. Alternatively, you can just type A. This will insert an anchor. Here, we can see that the anchor is given a specific displacement of 0.5 inches in y direction. Double click on the anchor, which opens the dialog box as given. Click on displacements and add the displacement of 0.5 inches in y direction for the operating case, that is T1. Click OK. This finishes the main run from node 10 to node 13. In the problem statement, you have a branch run from node 30 to 80. Let's do that now. In row 7, type C. This will make the row as comment row. Type 6-inch STD pipe as the comment. Click enter. In row 8, type 30 because that is where we are starting from, and use the type as from. Click F, that will automatically insert from, and click enter. From 30, the next element is 60 at a distance of 6 feet in X direction. So click tab, which will automatically update it to 60 node number, and the element type is pipe, so leave it blank. It is going in X direction by 6 feet, so type 6 feet. Click enter. On clicking enter, it is asking if we want to change the section. Click yes. Choose 6-inch nominal diameter or 6-inch as your section. Click enter. This will automatically update loads based on the previous row, that is at node 50 in row 6. In the next row, click tab, which will insert a node number 17, and the element type is a val. So you can either click here and choose val, or just type V, which will automatically select val. Val properties are not given. You can go ahead and select 250 pounds as the val weight, length as 2 feet, that is 24 inches. Additional weight, you can have 20 pounds, and you can have an offset of 3 inch in dy. Click OK. As you can see, graphics window is also updated. Click rendered shape to see the rendered view. Finally, in row number 11, click tab and type 6 in the X column and click enter. Also, node 80 is an anchor, so go here and type A and click enter. This finishes the modeling of your layout. You can see in the updated graphical window here, in rendered view and in line view. Again, it's a good practice to save the model here. Click save. From here, you can go to loads, click on load cases. By default, 4 load cases are already active: sustain, empty weight, expansion, and operating. Turn on design load case as well. Click OK. Clicking list icon opens a window consisting of all the like items that can be listed. For example, clicking on anchors here will list all the available anchors in our model. You can either edit the anchors from here, delete them if you want, and do everything from here. Also, clicking on bends will open a list of bends in your model. You may observe that the items in the list window are dependent on your model. These items will be populated based on the background model that you have defined. For example, if you have other supports like limit stops in your model, even those will be listed here, and you can select them for a list of limit stops. In our model, we have only these items that can be listed. Click OK. Click save and then go for analyze. Click yes to view the analysis results. The results window shows you 7 results. That is sorted stresses, port compliance, anchor report, support load summary, support loads, element forces, and displacements. This window again has items based on your analysis options. If you have other options selected in your input, then even those will come here. For our problem, we have only these reports that are generated by CAEPIPE. Click OK. The first result that shows here is of sorted stresses. Here we have separate field for sustained stresses and expansion stresses. You might have a separate field for occasional stresses if you selected occasional loads such as wave, wind, time history, seismic, etc. in your input analysis options. For this case, we have only sustained and expansion stresses. For the nodes with stress ratios greater than 1 are shown in red. We have computed stresses like SL and SV, allowable stresses like SH and SA, and stress ratios such as SL by SH and SC by SA for each case. You can click on S by A to plot the contours of stress ratios SC by SA here. If you need contours of stresses instead, you can click on S from here. This gives the contours of stresses for expansion case. Anytime if you want the contours for sustained case, click anywhere in the sustained field. This shows the stresses for sustained case. Clicking S by A again shows the stress ratios for sustained case. You can choose to have no color coding, which will just show the stress or stress ratio values. For example, clicking on S by A shows the stress ratio values at each node for expansion case. Clicking here will show the stress ratios for sustained case. Similarly, these are the stresses for sustained case and these are the stresses for expansion case. Next, we can choose the next result from here or use these navigation buttons. Click right arrow to go for next result and left arrow to go for previous result. Alternatively, you can also click tab to go to the next result and shift plus tab to go to the previous result. For now, I'll choose this button. This is the code compliance results. The element stresses and stress ratios calculated according to the selected piping code are shown here. Next, hanger report. The hanger report of only hanger, that is at node 30, is shown here. Number of column shows the number of hangers needed for this model. Here at node 30, it says that only one hanger is sufficient, which is of Grinnell type. Next is support load summary. Support load summary for each support is created by considering all the load cases and appropriate combinations with maximum and minimum as shown. This is the support load summary for anchor at node 10. You can go to next supports by clicking here and choosing from here or by clicking these navigation buttons. For example, this is the support load summary for hanger at node 30. Next, support loads are the loads acting on the supports by the piping system for the selected load case. Loads at the anchor for empty weight case are shown here. You can change the load cases by clicking here and selecting from here, or just use the navigation buttons like this. This shows the loads and anchors for operating case. Next, element forces. For the piping elements, element forces, moments, SIFs, and flexibility factors along with the operating stresses are listed here. You can click on the global forces icon to go to the forces and moments in global coordinates. You can click back to go to local coordinates. Next is displacements. The nodal displacements are shown here. Click on show deflected shape icon to see the deflected shape for this selected load case. You can choose the expansion load case and see the expansion deflected shape. You can click here on show animated deflected shape button to see the animation of the expansion load case. You can also see operating load case or sustained load case and so on. Finally, you can click on other displacements and choose, for example, min max. This will show the minimum and maximum displacements in all directions and the corresponding node numbers as shown. Now that all the results are finished, we can explore the print options available in CAEPIPE. You can choose what to print from here, or you can choose all options and You can either print to file in text format or CSV format, or you can click preview and print to a PDF. As you can see, cleanly formatted PDF with table of contents, analysis options, and all the selected results. And finally, bill of materials is prepared for you. You can close it. In this video tutorial, we have built a sample problem, applied materials and loads, analyzed it, and reviewed the results in detail. This workflow gives you foundation to model more complex pattern systems in CAEPIPE. Finally, if you would like to download PDF, mod, and results file that we just created, you can go to our website and click here, which will take you to our website called Pexit, which is a multilingual media platform for sharing files, ideas, etc. This is basically social media for professionals. You can log in, if not join, sign up. For my case, I'll just log in. Logging in will get you to exit home screen. You can go ahead and click software. Here there is a separate field for CAEPIPE tutorials. Click here. And from here, again, you can either download the PDF or the entire zip file. The zip file consists of the PDF, mod file, and results file as explained. With that, I think we're done. Thank you for watching and stay tuned for more tutorials. For any supports or queries, you can always reach out to us at support@sstusa.com. Thank you.